Can you see my screen?
Yes.
Okay. Good afternoon for everyone, dear professors, colleagues, and audience in general. It's a great pleasure and an honor to me to be here to present this article. Today I will talk about a specific analytical tool developed in my doctoral research called the Intravectorial Analysis. And the goal here is to raise a brief revision about it, and to bring up a few graphical relations between the intravectorial analysis and substitution operations. But first of all, this article and the another one that I will be talking about on Friday was written in Portuguese. However, for those who are not familiar with Portuguese, I will release English version of both articles on my personal site by Friday. And my personal site is www.andrecodeco.com. I invite you all to take a look over there. Okay. I should start talking a little bit about the research where this article and this subject, the intravectorial analysis, is contained. Well, the intravectorial analysis is an analytical tool from the sonic domain theory. But what is the sonic domain theory? What is this about? The sonic domain theory is a recent structured field of research linked to both composition and musical analysis. The sonic domain theory has its own compositional system, which is based primarily on three main concepts. First, the syncratic thinking proposed by Professor José Alac in 2013. He's a professor in National University of Cordoba in Argentina. In second place, a unique perspective about time and space in music, taking assumptions about time itself from Dr. Lynn Moly. He is an American physicist who I think he's working in Canada right now, and concepts proposed by Xenax in his book Formalized Music. The third concept in this is the Pinto-Beira's approach of systemic modeling. There is several articles written by Pinto-Beira regarding systemic modeling, and you can find more information about it on my thesis, also available on my site. These three approaches allowed me to build a compositional system, or a system of composition. Yet, they have inspired me to build several analytical models, all based on mathematical modeling, such as perturbation index, subsidiary perturbation indexes, the intravectorial analysis, linear and multilinear interactions, and the derivative algebraic description. In this presentation, we will take exclusively the intravectorial analysis and its graphical relations on substitution operations. Once again, for more information about all analytical mechanisms and the compositional system, please take a look on my thesis available on my site. Once the sonic domain is briefly exposed, let's take a deeper look on some preliminary notions. First, the PACS matrix notation. PAC means literally expressive compositive potential. It's about a musical idea and its essential feature, something that can be understood as a primary musical material. The PAC is constituted by the confluence of three parameters: pitch, time, and dynamics. We use a matrix to describe the PAC as a set of vectors. As we can see on the example, on the first row, we plot the pitch component. On the second row, the time component. On the third row, the dynamics component. Vertically, we have the vectors that compose the matrix. As we can see, the pitch component is described using pitch class set theory. However, we are considering all registers. I mean, we operate on the p-space according Morris approach. For the time component, we just assume that the quarter node has 1 second of duration, and by this, all nodes are proportionally divided. Considering the dynamics component, we are using a specific table which can be assessed on my thesis. On this paper, we will treat only pitch component in an attempt to be more direct and clear. So this figure, which is the first measure of Sirin from Debussy, reveals how music material can be transcribed on a PEC matrix. Okay, so the intravectorial analysis now finally we will see some preliminary notes about the intravectorial analysis. Here is the algebraic description of it. You can see on the right side of the screen. So the intravectorial analysis in the mathematical sense, it's simple a subtraction operation. We take a pair of elements from a component and we apply this subtraction. We do the last element of the pair and we subtract from the first one. In the specific case of the shown figure, we do 9 minus 10, 11 minus 9, and so on. It's clear how it works. So let's say, you can see now how this operation works. So let's say the set S is the set of intravectors coming from the subtraction operations. As we can see, the intervector U has a negative number. That's not a mistake. In fact, regarding pitch components, the negative number tells us that tells us that happened a downward interval. More than that, because we are using p space, negative numbers reveal the exact amount of half tones from a pitch to another was taken. Thus, here we have not so a clear understanding of the direction took, but also how many steps in that direction was took. On time component, we also can see a negative number. Of course, it's not a negative time. It is just revealing to us the second time element, or the second element from the time component is running faster in relation to the first one. So negative numbers in this case, in the temporal component, are revealing faster and or slower nodes. In other words, we can see the amount of space consumed by each element. And that is, in fact, the concept of derivation in mathematical sense. But there is a number 0. I'm sorry, now you can see the numbers. I'm sorry. But there is a number 0 on the dynamics. I'm talking about these numbers on these blue circles, all right? Those are the intervectors. But there is a 0 number on the dynamics. Well, 0, it's a very important number on the scope of the sonic domain theory. 0 means no perturbation of the space, which is there's no changing happen. There is a very important thing about musical analysis because it can mean that break of expectation, for example. We have no changes on time. If we have no changes on time component, for example, there's no sense of direction, for it's not possible to distinguish events by relations as higher or less than, before or after than, and so the causality relation is lost. Of course, we are talking about a musical scenario where every pitch, time, and dynamics are the same. However, even when 0 appears on the time component and just on the time component, we shall perceive the lack of perturbation. So in this slide, we can see all kind of transformations on the scope of the sonic domain theory. We have three main categories of transformation, and Toussaint reviewed all of them on his book. In this paper, we will take only 4 of 6 substitution operations. You can see more about all of them in my thesis again. We are taking from now transposition, inversion, retrogradation, and rotation. Our goal is to see graphical relations between intravectors and these specific operations. So these are the operations we are taking from now, okay? So now we can see the first algebraic description of transposition operation. On the right side, we can see a small musical, you can see a musical example. In other words, transposition is a mathematical operation. I mean, an adding operation. We add some scalar to an entire component, and then we have the transposition, as we can see how was done on the example. Applying intravectorial analysis, it's shown the first relation. I mean, the intravectors are exactly the same, as you can see. U, it's equal to V, right? But it's not just that. Let's take the first element of the intravector and assume the number is a point on a horizontal x, on the x-axis. We have a point of this kind, 2 and 0. And taking out the second element of the intravector, we have another point, 0, 1. That gives us 2 points, and so a straight or a line. From this line, we can take a simple function here called f of x. So connecting the intravector u to the function f of x, the intravector v to the function g of x, we have that f of x is equal to g of x. We will use this elucubration for every two-dimensional graphical all graphs coming, right? Taking out the inversion operation, we can see its algebraic description on the left side, and the intravectorial analysis on the right side. A new relation arises. I mean, now the intravector v is minus u. That was expected. I believe you can think. But applying the two-dimensional graph, actually, we have a rotation function, mathematically speaking. So also g is equal to minus f. Well, that's okay about symmetry. But when we take retrogradation operation...
Andrea, please let me stop you for a minute. You have 1 minute 30 to close.
Okay.
Sorry.
I'm almost finished. But when we take retrogradation operation, natural or common graphical expectation does not come naturally. Before we see why is that, in fact, we can get a path from intervector to another. In fact, if we apply the first an inversion, then a retrogradation, and then another inversion, if we can jump from the intravector u to intravector v. However, this is a big path. There is another way, and we will show we will show it on the next slide. So u is not equal to v. So that's the relation. But now let's see if really the symmetry doesn't come naturally. As we can see, neither the intravector u is equal to the intravector v, and f keeps relation with g. However, we should expect some symmetrical relations here, okay? Well, the symmetry in this case is not on the intravector itself or on the functions. Indeed, is the norm of that is the norm that is the same. Now, we also have a simple formula that allows us to jump from the intravector U to intravector V, and this is the formula. That's the formula we found linking to these two intravectors. Finally, we got the rotation operation. The algebraic description on the left side is on the left side, and the intravectorial analysis is on the right side. So in this case, nothing is symmetrical. Intravectors are not equal, neither the functions and the norms. That's because the similarity relation regarding the rotation operation is deeper than the other ones. We are using the same elements, the same set of pitches, but either in sonic ways, in concrete ways, and in abstract ways, I mean, in mathematical ways, the similarity is not so easily perceived. However, there is a relation between the intravectors, as we show now. There is a simple formula that can be applied to jump from intravector U to intravector V. It's at the bottom of the screen. Finally, our conclusions are, there is a clear relation between intravectors and the graphics present. This allows us to assume that we can measure symmetry using intravectorial analysis. In other words, every trace of similarity on a musical example will be shown by intravectorial analysis. That said, intravectorial analysis is a useful analytical tool. Secondly, we assume that it's not so easy to manipulate this tool. The next step should be design a computational app to test and to force the intravectorial analysis in a way that musicians and people in general can see all similarities or relations of similarities in some musical example. Since the sonic domain theory and its analytical tools are meant to be used and reflect what happens on the concrete level of the music example. That's the reference, and thank you for watching.